Okay, so this is our first lecture, and this is first lecture will be on Maxwell's equations. So let's discuss about Maxwell's equations. So we shall proceed in a quite similar order that we must have seen before. That is, we shall first start with electrostatics. Okay. So our intention is to proceed to the general picture as quickly as possible. So we already are familiar with the Coulomb's law, and by the way, I forgot to mention, if I haven't mentioned, that we are using Gaussian units, and I shall discuss about the conversion of units between SI and Gaussian units, or you can find it anywhere in any textbook. So Gaussian units are preferably the good units for any theoretical physicist. Or when it's come to engineering, we talk about the SI units. So the interaction energy of in an empty space, in an otherwise empty space consisting of charges, or in a vacuum that you should call it, and is equal to half summation over A and B, A not equals to B, EA EB divided by R AB, where EA is the charge of the eighth particle and EB is the charge of the bth particle, and RAB is the distance between the separation between the eighth and the bth particle. Well, I've summed half over here because you're going to get a double summation, so you're then going to get everything twice. So that means you put a half over here and you're done with the job. So that was about the interaction energy. Now I shall write it in a different form. I shall write it as half summation over A EA summation over B not equal to A of EB by RAB. So what I did is just I pulled out the summation over A of EA from the sum, and I shall write this part as phi of A. This is called the electric potential at a location of the eighth particle, and so this can be written as half summation over A EA, or I'll not write it as phi of A, I'll write it as phi sub A, sub phi A. Now this expression, okay, there is some minor significance of this. there is some minor significance of this equation. If you see this equation, this is called equation is called the interpretation of electrostatics, or force fields at action at distance point of view. Okay, so this is the first way to interpret force fields. Another approach is called the field concept, and this is due to Faraday. So field concept is basically, it says that whether or not the particle is there, the field is everywhere. Okay, and so you can transport energy, you can interact, two particles can interact with the help of a field. This is called field concept. And for example, apart from classical electrodynamics, you can have something called quantum field theory also, which is nothing but a field concept. So it's nothing but a quantization of fields. So it's nothing but the generalization of classical field theory to quantum field theory. So field is basically a local quantity, whereas action at a distance point of view is a universal concept. So at action at a distance, as Newton used to say that gravity acts instantly, but then Einstein came and he said that no, gravity propagates at the speed of light, so it's not immediate. There is nothing called action at a distance, according to Einstein. So, but of course, in this case, we can take for our convenience the action at a distance point of view or the field concept. Now we take a step in this direction by considering the potential as a field. Now what is a field? It can be a field of something. So now let's name it. Let's take it the potential. And since a field is a local quantity, it must be defined everywhere. So this is phi of r. This is simply the potential. This is simply, we call it the potential. And we simply call it the potential, and this is defined by phi of r is defined by EA by RA by RB. So this is called the potential, and this is you could have a bunch of charges, so you could put a summation over here. So if you are not seeing it properly, this is summation over B EB divided by RA minus RB. These are vectors. Okay, so this is basically the field, potential field that we are defining. Now, this equation that we had earlier derived, now we cannot say that this potential and this potential are the same, because this is action at a distance and this is a field, remember. So what happens, what is the characteristic property, and maybe you can call it a demerit of the field concept, is that there is a chance of self-interaction. There is always a chance of self-interaction. So what happens in self-interaction? Self-interaction is basically the energy, the interaction energy now can be written as summation over A EA phi of R minus, so this is separate, sorry, summation over A summation over A EA phi of R. But this is not a correct equation, because a single particle EA is being summed over, and maybe the potential this includes the particle A also. So it's basically saying that the particle A is acting on itself, which is not possible. Hence we need to subtract some term from this, that we shall call summation over A EA, that is interaction energy of A with itself. So this is to be understood as not understood numerically. This is not to be understood something numerical. This is to be understood just as an injunction as to remove the self interaction contribution from the particle. Okay. That was about the two concepts and the field concept and everything. Now we shall move forward, and I'll tell you that the self interaction was a threat here, but in some quantities, like deriving the force, it is not a threat anymore, and that is something that can be proved mathematically. That is something that can be mathematically proved. So if you have the notion of force can be derived from energy, and that is del E equals to the gradient with respect to A of E times rho A. So this is the equation. So what I did is I just took a variation of E, and that is the gradient of E times the variation of R times the variation of R. So the variation of R, the gradient of E is something we recognize, and that is basically the negative of the force A. This is minus FA times the variation in R. Now comparing this with the initial expression we had on energy, that was half of summation over AB, half of summation over AB, A not equal to B EA EB by RAB. So we have this equation. So that equation and this equation. So if we compare that, we could write it as, realize that we could write it as FA is basically the gradient of with respect to A of the gradient with respect to A of summation over A EB RAB, and if we pull out is the gradient with respect to A, we pull out this, we have EB by RAB, and then we have gradient over A, gradient of over A of E of A phi of at the point RA. So in the last form, what we have last step what we have done is we have employed the field concept instead of the action or distance concept. And in the last form we have did this, but initially you would argue that we started from something that is an action and distance point of view, and we landed upon something that is a field concept. So this would contain maybe an extra self-interaction term, but that is not true. And to make you see why that is not true, let me ask you mathematically, what is this additional unwanted term that we are talking about? It is basically summation over I think summation over EA. So we have, I think this is the self-contributing term. So we have EA divided by RAB. So you have RA minus RB and R minus RA, or you can say you have R minus RA. That is what these this thing is basically phi of I is this is basically EA by phi of R minus RA. So that is the thing, and this in the limit as R goes to RA. Okay, so if you take the gradient of this and mathematically if you say the gradient with respect to A of R minus RA, R minus RA, so this is something that you could treat probably this is something that you could get easily, with a minus sign, of course, since this is a 1 by x form, so you will get minus 1 by x square. So what you will get is minus 1 by x square. So I would like to write that in this form. Since this is the same thing, if this would be squared, so you can see that this is the same thing basically. So as you can see that, and since so I'll take this here, and what I did is just took the gradient of this term. So I took the gradient with respect to A of this term, and since I have the minus sign already, minus cancels. One minus here and a minus here, it cancels. So what I have is now EA squared times R minus RA divided by R A. Sorry, I think I wrote it wrong.